Hello everyone, my name is Tilman Milzo, and I'm talking about peeling and nibbling the cactus, sub-exponential-time algorithms for counting triangulations. This is joint work with Daniel Marks, and we are both from the Hungarian Academy of Science, MTA Stucky. Okay, let me get started with my course. So this is Daniel Marks. Um, okay. Um, Okay, now let's go to the definition of a triangulation. Given a set of points in the plane, a triangulation is a maximal set of non-crossing line segment, and as you can see, each bounded face will be indeed a triangle in that case. And that is how we define triangles in this talk, a triangulation in this talk. And there has been some previous work on counting triangulations. 3 years ago, there was an algorithm of Alvarez and Seidel who showed there's a 2 to the n squared algorithm, and they won the Sausage Best Paper Award. And this is a picture of Alvarez, and this is a picture of Seidel, the best one I could find. And we could significantly improve this result by making it sub-exponential, so we could find an algorithm with running time n to the over root of n. And in the remainder of the talk, I want to explain you the key ideas of that algorithm. Before I do this, note that this constant here in this O seems we can prove is upper bounded by 11. Maybe it's one could, with a little bit more effort, bound it even better. But yeah, only once you reach around 100 points, this algorithm might actually outperform the algorithm of Alvarez and Seidel. Okay, let's start. Before I can explain, or I want to explain you the algorithm to count triangulation, let's look at a problem which is very similar, namely minimum weight triangulations. So here the aim is to find a triangulation such that the total edge length is minimized. So there's an algorithm of Lingas from 1998, which works as follows. You take your set of points, so you know in your triangulation already the outer face, well, all the edges must be present there, and then you guess a balanced separator. So you know each triangulation has a balanced separator, and you know your minimum weight triangulation also has a balanced separator. So you guess all potential balanced separators, and one of them will be the balanced separator of your minimum weight triangulation. So, and you know balanced separators have size over root of n. So you guess all of them, and for each of them, you have an inner problem and an outer problem, and you recurse on those. And so since each separator has length over root of n, the total number of separators is n to the over root of n. So they already exist for this. Okay, now let's go to the runtime analysis. The runtime is bounded by n to the over root of n times twice for both subproblems, but this twice already lies in here, and then you have to solve a geometric series in the exponent, and you get an n to the over root of n total running time algorithm. Yes, so there already exists algorithm with sub-exponential time running time for similar problem for triangulations, but instead of counting, you want to have minimum weight. And the first thing I want to tell you is that our algorithm works very similar, but from a very high level. I want to tell you why the algorithm of Lingas doesn't work for counting triangulations. So this is the insight I want to tell you now. So why does it not work for counting? Let's say you have your minimum, or you have some triangulation, right? So we don't want to just consider the minimum weight, but all triangulations. Then this might have actually two balanced separators. So if we guess all separators, we would guess both of them. And in that case, we would double count the specific triangulation. So what we need is, we want that for each triangulation there should be only one separator, and we want to guess only that one. So a natural approach would be to say, okay, we take the lexicographically first and so on. This would mean we somehow encode this in a string, and then for these two, we can say one of them is the lexicographic first one, and then maybe we would only guess a red one and say no, the blue one we don't guess. But it's very difficult because maybe the blue one would be lexicographically first separator for different triangulation, so we also have to guess it, but then we have to infer that this triangulation there will not be counted, and we don't really know how to do that. It seems for us very unclear how to do this. Also the same with the isolation lemma, which would be a different approach. We have no idea how it could work. Okay, so what shall we do? Okay, let's take a step back and look at the algorithms that were done previously. So all of these previous algorithms, they always used separators in the same way that will use separators, and that you saw separators being used. But they had the problem of being canonical, or they needed to be canonical in a way that they could be used in an algorithmic scheme. Okay, and the way they define their separators is in terms of the point set. From our point of view, so I've been told that Alvarez and Seidel also thought about their separators as being defined in terms of the output, but we didn't know that. So what we did is we concentrated on trying to identify separators in the output, namely the triangulations. And what turned out to be the case is that we could identify two different kinds of separators and made our algorithm adaptive, namely if we had this kind of triangulation, we used that separator. If we had a different kind of triangulation, we used a different separator, which was not possible by any of the previous algorithms that were there. Okay, so let's go more into these algorithms. So the main concept of our algorithms are layers. So I will tell you first a concept that is very well known, namely that of onion layers. So onion layers are defined as follows. You've given a set of points, and the first layer is the boundary of the convex hull, and then you remove it, and then you take again the boundary of the convex hull for the next layer, and so on and so forth. And now what we do is we take this concept and we apply it to triangulations. So we take all the edges and faces incident to the outer face, so that would be here those, and remove them. So here in that case it's the same, right? But once we remove them, we remove also these edges, which are maybe incident to a vertex on the outer face, but this edge itself is not incident to the outer face. And then already the second layer C looks different, and so we go in that same fashion we define all the layers. So here is interesting, these layers are different. As you can see here, we have on the right side we have only 4, on the left side we have 5. And it turns out that all these layers are cactus graph. Each layer by itself is a cactus graph, and that's why we call these layers cactus layers. And yeah, so let's see what we can do with these layers. So the first thing we can do is, in case we have few layers, let's say only 4, we can find path separators. Path separators are paths from the inside to the outside. So at first, let's just see how they are defined, and let's see later how we can use them in an algorithmic scheme. So we just start from any vertex in the interior, and we go in each step one layer further to the outside. And so there are many ways to do that, but the key observation is that these paths are short. So if we have few layers, so they're bounded by the number of layers. As I already said, they're not unique, but there's an easy way to make them unique. Namely, we use a label on each vertex, and then whenever we have the choice to which vertex we go farther, we choose the one with the lowest label. So let me illustrate this. Here we start with that vertex, and we have 4 neighbors, and one of them has the lowest label, and that vertex we continue on. And then so on, and we're in the next vertex, we have two neighbors to the next layer, and then we choose the one with a lower label, and this way we get unique parts to the outside. And okay, and these constraints can be implemented in an algorithmic scheme because these are local constraints only on the path. And now the paths are unique. And this idea is actually not new. So this has already been done by Alvarez, Bringman, Radu, and Sharab-Ray, and they did it for onions. And the only thing that we did is basically say, okay, it also works for cacti instead of onions. So basically half of our papers is their paper. But yeah, it's still good, I think. Okay, but our advantage is cacti are adaptive, onions are not. So let me explain now how this algorithm, how these separators can be used in an algorithmic scheme, and we call these algorithm nibbling. So let's nibble. Okay, let's see how that goes. So if we want to start this algorithm scheme, we have to choose an edge here, this green edge, and say from that green edge we start nibbling. And the way we do this is we guess all potential triangles incident to that green edge. So here I drew only one, and then from that vertex here, which is opposite to that green edge, we shoot the outgoing canonical path. And in that way, we have two subproblems. So one here is this really big one, and the other is this tiny one. So somehow you could think of the big subproblem just get a little bit smaller. And then recurse. So we have again this new green edge for the big problem. We guess a triangle for it, and then from the other vertex we guess the canonical outgoing path. Again, it has only like one, so it's not very spectacular. And here is the left subproblem is a little bit larger, but still pretty small, and the big subproblem just gets reduced in size a little bit. And let me show one more recursion step, and you see here now already this got bigger, and this canonical outgoing path is length 2. And then we would start recurse from here, and then actually we might split this problem into two subproblems of roughly the same size. Note that these that this separators are not balanced, but this is not a real issue. Yeah, and then it continues. Yeah, we call this nibbling because we always make the big subproblem a little bit smaller by removing small bits of it. Okay, so now I want to come to the second algorithmic idea, namely using layers itself as separators. So as I said, if we have few layers, then these paths are really good. So, but what happens if you have a lot of layers? Well, if you have a lot of layers, then one of those layers is going to be small by the pigeonhole principle, right? So if I have here 1 million layers, then one of them has n divided by 1 million, size of n divided by 1 million, and that's going to be small for whatever. Okay, and then we use this one. And so to make this choice unique, we choose the first layer starting from the outside. So we check the first layer, okay, this is big, and the second layer, okay, this is, okay, they're already small, so we take it. And this makes a unique choice. And then we have to be careful because now, okay, now we choose this, and we want to count all these triangulations in here and the triangulation in there. But we want to make sure, so for the inner we don't really care what happens, but for the outer we want to make sure that really this was the first small layer. So we have to add layer constraints which basically say we guess the size of these layers, and they must be large. And this does not work for onions because yeah, or I mean I would not know how to define this for onions. And we call this peeling, because basically we remove all these root of n outer layers. Yeah, and yeah, we thought that's a good metaphor. Okay, so what is this algorithm looks like from a far away perspective. So we take our subproblems and we look, okay, how many layers do we have? If we have few layers, we start nibbling and we continue this algorithmic scheme that I indicated. If we have many layers, when we do the peeling, because one of these layers is going to be small, and then we go back to the main routine for both subproblems. Okay, so let's go a little bit more into detail, namely, what does our subproblems look like? Oh, sorry, first a remark. So small means smaller than root of n, big means larger than root of n. Okay, so the structure of our subproblems is basically what you would think of it. But note that we, in some cases, have to add layer constraints, in other cases not. And we also have to guess some width information. Yeah, and then we want to triangulate a certain region and a certain region not, and certain boundary constraints. Okay, and so if we want to nibble, then these subproblems look even more complicated. So we somehow have to maintain from where we start nibbling and which boundary passes we already have, and then some local constraints, and then layer constraints and width information. But so it gets complicated, but it's doable. And let me briefly repeat how such an algorithm looks like. So here we have our problem, and we guess our layer or small layer, and then we have an outer problem and an inner problem. The inner problem might be split again because a cactus graph might have several bounded faces. And in our outer problem, it stays simple, so there's only one outer face. And then here for the outer problem, we will add layer constraints, and note that we start from problem where we did not have layer constraints. And here for the outer problem, we suddenly have small width, so here we only have to nibble, and for these we don't know. We could recurse either way. And then, okay, if we want to start nibbling, all we have to do is we have to specify an edge from where we start nibbling, and initially these boundary paths going to be degenerate to have length 0. But that's straightforward. So for this nibbling, yeah, in general it looks like this. As you already can imagine, we guess this triangle, and then we guess our outgoing path, and then we split into two subproblems. But even more, we also have to guess our constraint decomposition. I didn't notice. So we have layer constraints, and we have to say now, okay, how many vertices are on that layer, how many vertices are on that layer. And well, this is easy because we know exactly that only these vertices are shared, and there are also some problems with this inner layer, which might be split up. But okay, I will not go into that here. And now, just before I finish, let me go through the runtime analysis. So in the nibbling case, right, our paths are short. In the peeling case, our layers are small. So either case will apply. And then note that if we have few layers, then also our number of layer constraints is small. So this is also fine. And in this way, we can bound the total number of subproblems, because each subproblem is defined by 2 layers and 2 paths, basically, and layer constraints. But for all of those, there are not so many, only this many possibilities. You multiply all of them, and you get this bound, and here you get that bound. So things are fine. And the total number of recursions, well, you guess a short path, right? So we already saw that this will be this, and here you will guess a short layer, so this is this. And then for the total runtime, you'll multiply the number of subproblems times the number of recursions, and that's what you do. And this finishes my talk, and I thank you for your attention.